You create two particles. You send one to Tokyo, you send one to New York, 10,000 miles apart. Then you measure one of them. Instantly, immediately, faster than any signal could possibly travel, the other one changes. It responds. It knows. People call this spooky action at a distance. Einstein hated it. Physicists argue about it. Pop science articles call it magic, call it proof that everything is connected, call it evidence that consciousness shapes reality. And Richard Feynman would tell you they're all missing the point, because quantum entanglement isn't magic. It's not mysterious in the way people think. It's just quantum mechanics doing exactly what quantum mechanics does. And once you understand what's actually happening, the spookiness disappears. But here's the problem. To understand what's actually happening, you have to let go of something fundamental, something so basic to how you think about the world that you probably don't even realize you're assuming it. You have to let go of the idea that particles have definite properties before you measure them. That's the assumption. That's what makes entanglement seem impossible. And that assumption is wrong. Let me start simple. You have a coin. You flip it. While it's spinning in the air, does it show heads or tails? You might say neither. It's spinning. It doesn't show anything yet. But you probably still think the coin has two sides. And when it lands, it'll reveal which side was which. The coin had properties all along. You just didn't know them yet. Quantum mechanics says no, not for quantum objects. An electron doesn't have a definite spin before you measure it. Not that you don't know the spin, not that it's hidden. It doesn't exist as a definite property. The electron is in a superposition, a combination of both possibilities. Spin up and spin down simultaneously. Not one or the other, both. And only when you measure does one outcome become actual. You might think this is philosophical. Nonsense. Just words. But it's not. We can test this. We can do experiments that distinguish between the property exists but we don't know it, and the property doesn't exist until measured. And the experiments are clear. Absolutely clear. The properties don't exist beforehand. Measurement doesn't reveal a pre-existing value. Measurement creates the value. This is what Feynman meant when he said nobody understands quantum mechanics. Not that the math is hard. The math is fine. It's that the implications contradict our deepest intuitions about reality. We think things have properties, positions, velocities, spins, colors, something. But quantum mechanics says no. Between measurements, particles are described by wave functions, mathematical objects that give probabilities for different outcomes. Not probabilities because we're ignorant, probabilities because that's all there is. Now, entanglement. You create two particles in a special way so their properties are correlated. The standard example is spin. You create two electrons in a state where their total spin is zero. If one is spin up, the other must be spin down. If one is spin down, the other must be spin up. They're perfectly anti-correlated. Now you separate them. One goes to Tokyo, one goes to New York. They're now 10,000 miles apart. You measure the Tokyo electron, you find it spin up. Instantly you know the New York electron is spin down. That seems fine. That's just correlation. If I tear a piece of paper in half, put each half in an envelope, and mail one to Tokyo and one to New York, when you open the Tokyo envelope and find the left half, you instantly know New York has the right half. Nothing spooky about that. But here's the difference. With the paper, the left and right halves existed before you looked. The properties were there all along. You just didn't know them. But with the electrons, the spins didn't exist before measurement. Neither electron was spin up or spin down. They were in a superposition. Both were in an undefined state. And yet when you measure one and find spin up, the other is definitely spin down. Measure one and find spin down. The other is definitely spin up. Every single time. Perfect anti-correlation. Even though neither had a definite value before measurement. That's entanglement. That's the weirdness. How can particles with no definite properties be perfectly correlated? How can measuring one seem to affect the other instantly across any distance? Einstein called it spooky action at a distance. He thought it proved quantum mechanics was incomplete. There must be hidden variables, he argued, properties the particles had all along that we just couldn't see. But he was wrong. We know he was wrong because of Bell's theorem. John Bell, in 1964, proved something remarkable. He showed that if particles had hidden properties, if the values existed before measurement but were just unknown, then the correlations between Measurements would obey certain mathematical inequalities, Bell inequalities. And if quantum mechanics was right, if the properties truly didn't exist until measurement, the correlations would violate those inequalities. So we tested it over and over, different experiments, different setups, different particles, and the result is always the same. Bell inequalities are violated. Nature breaks the rules that hidden variables would have to follow. The properties genuinely don't exist before measurement. Quantum mechanics is right. Einstein was wrong. There are no hidden variables. So what's actually happening? How do you explain perfect correlations without hidden properties and without faster than light signals? This is where Feynman's way of thinking helps. Stop asking what's really happening behind the scenes. Ask what the math says. What can we predict? What does the wave function tell us? When you create an entangled pair, you're not creating two separate particles with correlated but hidden properties. You're creating one quantum system, a single wave function that describes both particles together, not particle 1 plus particle 2. One combined system. The wave function doesn't say particle 1 is spin up and particle 2 is spin down. It says if you measure particle 1 as spin up, then particle 2 will be spin down. And if you measure particle 1 as spin down, then particle 2 will be spin up. The correlations are built into the single combined wave function. The particles aren't separate in the quantum description. They're described together as one system. Even when they're separated by thousands of miles, the wave function treats them as a unified whole. That's what entanglement means. Not that measuring one sends a signal to the other, but that there's one quantum state describing both. When you measure the Tokyo electron, you don't change the New York electron by sending it a signal. You change the wave function of the combined system. The measurement collapses the superposition. Before measurement, the system was in a state of spin up here and spin down there, plus spin down here and spin up there. Both possibilities at once. After you measure and find spin up in Tokyo, the wave function collapses to just spin up in Tokyo and spin down in New York. The New York electron didn't receive a signal. The description of the system changed. You might protest. You might say that sounds like word games. How is that different from magic? But it's different because of what you can and cannot do with entanglement. And this is crucial. This is what people always get wrong. Entanglement does not allow faster than light communication. You cannot use it to send information. You cannot affect the other particle in any way someone else could detect. Here's why. When you measure the Tokyo electron, you get a random result. 50% chance spin up, 50% chance spin down, completely random. You can't control it. You can't choose which outcome you'll get. Now, once you get your result, you know what the New York measurement will show. But the person in New York doesn't know you measured, and they can't tell by looking at their particle. If they measure, they also get a random result. 50% spin up, 50% spin down. Their results look completely random. Only when you compare notes, only when you bring the results together through normal, slower than light communication, do you see the correlation. Every time you got up, they got down. Every time you got down, they got up. The correlation is there. It's real. It's perfect. But you can't use it to send a message because you can't control your outcome. You can't decide to make yours spin up so theirs will be spin down. You just measure and get a random result. They measure and get a random result. The results are correlated, but neither party can see that correlation without classical communication. This is what Feynman emphasized. Quantum mechanics is local in the sense that no observable effects propagate faster than light. You can't use entanglement to send signals. You can't affect anything at the distant location in a way that could be detected there. The correlations exist, but they're only revealed when you compare measurements, and that comparison requires ordinary communication. So what violated locality? What travels faster than light? Nothing physical, no energy, no information, no signal. What changes is the wave function, the mathematical description. But the wave function isn't a physical thing. It's not located in space. It's not made of matter or energy. It's a mathematical object that encodes probabilities. And updating a mathematical description isn't a physical process. Think of it this way. You have a pair of gloves. You put each in a box without looking. You ship one box to Tokyo and one to New York. The moment you open the Tokyo box and see a left glove, you instantly know New York has the right glove. Your knowledge changes instantaneously, but nothing physical traveled. No signal went from Tokyo to New York. You just updated your information. Quantum entanglement is similar, except the gloves don't have left or right-handedness before you look. They're in a superposition of both, and yet when you look at one and see left, the other is definitely right. The correlation is perfect even though the properties didn't pre-exist. That's the quantum weirdness, but it's weirdness about the nature of properties, not about signals or communication. Feynman worked extensively on this in his own way. He developed quantum electrodynamics using path integrals, and in that framework, particles can even interact backward in time in the math, but those aren't real faster than light or backward in time signals. They're mathematical contributions to probability calculations. The distinction between the math and the physics matters. The math can include all sorts of things that don't correspond to observable signals or causes. The same applies to entanglement. The wave function describes the system. It evolves according to equations. It includes non-local correlations. But those correlations don't translate into faster than light observable effects. They're constraints on what measurements will show, not causal influences. Now, people sometimes bring up consciousness. They say the observer collapses the wave function, so consciousness must be special, must be affecting reality, must be connected across space through entanglement. Feynman would have no patience for this. Observer doesn't mean conscious being. Observer means anything that interacts with the system in a way that could, in principle, record information. A detector is an observer. A photographic plate is an observer. A rock, if the particle bounces off it in a way that leaves a trace, is an observer. Observation is physical interaction, not consciousness. When you measure an entangled particle, your measuring device interacts with it. That interaction entangles the device with the particle. The combined system of particle plus device no longer has the same quantum correlations with the distant particle. That's what breaks the entanglement, not your awareness. Physical interaction. Decoherence is the key. When a quantum system interacts with a large environment, the environment acts like a measuring device. Information about the quantum state leaks into the environment, gets spread among countless particles, becomes irretrievable. And that suppresses quantum effects, makes things look classical, breaks entanglement. Two entangled particles in perfect isolation maintain their entanglement forever. But any interaction with the environment, even tiny interactions with air molecules or stray photons, causes decoherence. The entanglement degrades. The correlations weaken. Eventually the particles behave classically, not because of distance, because of interaction with environment. This is why entanglement is so hard to maintain, why quantum computers need to be so carefully isolated, why quantum experiments require extreme conditions. Not because entanglement is magical and fragile, because any interaction with the environment causes decoherence, and decoherence destroys the quantum correlations. Feynman understood that quantum mechanics requires a different way of thinking, not just new equations, a new conceptual framework. You can't think of particles as little balls with definite properties. You have to think in terms of wave functions, probability amplitudes, superpositions, and when you do, entanglement stops being mysterious. It's just what happens when you create a system in a superposition that involves multiple particles. The system is one quantum state, not separate particles with separate states, one combined state. When you measure part of the system, you collapse the superposition. The rest of the system responds not because you sent it a signal, but because it was never truly separate in the quantum description. The real mystery isn't entanglement. The real mystery is measurement. Why does measurement give one definite outcome instead of a superposition? Why does the wave function collapse? Or does it? That's where interpretations of quantum mechanics differ. Many worlds says it doesn't collapse. Copenhagen says it does. Pilot wave theories add hidden variables of a different sort, but all the interpretations agree on the predictions. They all give the same experimental results. They all say entanglement exists. They all say it doesn't allow faster than light communication. The differences are about what's really happening, about the underlying ontology. And Feynman's view was that we should focus on what we can measure. The interpretations are interesting, but the physics is in the predictions, and the predictions are tested constantly. Quantum computers use entanglement. Quantum cryptography uses it. Experiments violate Bell inequalities routinely. We're not speculating about whether entanglement is real. It's real. It's useful. It's understood mathematically. What remains debated is what it means about the nature of reality. Does it mean reality is non-local? In some sense, yes. The wave function doesn't respect spatial separation, but observable effects are local, no faster than light signals. Does it mean particles aren't real? Depends what you mean by real. They're real in that we can detect them, but they don't have definite properties between measurements. Does it mean everything is connected? Again, depends on what you mean. Quantum states can be connected through entanglement, but that doesn't mean measuring one particle affects your consciousness or destiny or anything mystical. Feynman was always clear. Quantum mechanics is strange, genuinely strange. It violates classical intuitions, but it's not magic. It's physics. Precise, mathematical, testable physics. The strangeness comes from nature being different than we assumed, not from anything supernatural or mystical. When you measure an entangled particle, you're not sending telepathic signals across space. You're interacting with a quantum system. That interaction changes the wave function, and because the wave function describes both particles together, the description of the distant particle changes too, but no signal propagates, no energy travels. The correlation was already there, built into the quantum state from the moment of creation. Think of the wave function as a set of rules for what measurements will show. When you create entanglement, you create rules that say these two measurements will always be correlated in a specific way. Those rules don't depend on distance. They're properties of the wave function itself. When you make a measurement, you learn something. You update your knowledge of which rule applies, and that tells you what the other measurement will show. But the rules were there all along, encoded in the quantum state. Measurement doesn't create the correlation. It reveals it. Or more precisely, it actualizes one of the possibilities that was in superposition. And because the possibilities were correlated, the actualization is correlated too. This is hard to wrap your mind around because it requires accepting that possibilities are real in some sense. That superpositions aren't just ignorance but actual physical states. That a particle can genuinely be in two states at once until measured. Our brains didn't evolve to think this way. We evolved to deal with macroscopic objects that always have definite properties because they're constantly being measured by the environment. But at the quantum level, different rules apply. An entanglement is just those rules playing out. Two particles, one quantum state, correlated outcomes, no signals, no magic, just quantum mechanics. You create two particles. You separate them. You measure one. You know what the other will show. Not because you sent it a message, not because consciousness connected them, because they were never truly separate in the quantum description. They were always one system, and that's what entanglement is. Feynman would tell you to stop looking for classical explanations. Stop trying to make it make sense in terms of balls and signals and hidden properties. Accept what the math says. Accept what the experiments show. Quantum mechanics is how nature works. And once you accept that, entanglement isn't spooky. It's just quantum. The particles are entangled. The correlations are perfect. The wave function describes both. And there's no magic involved. Just the strange, beautiful, testable reality of quantum mechanics.